Namaste, one and all. My name is Arvind Joshi. I'm assistant professor in the Department of EEE, PVIT, Mysore. In the previous videos, we actually observed about uh, design and analysis of voltage follower, inverting amplifier, non-inverting amplifier, and then frequency response of second experiment, frequency response of inverting and non-inverting amplifier, like that. In this video, let's discuss about design and analysis of operational amplifier based RC phase shift network. Okay, yes. Aim of the experiment, operators required, theory, and then circuit diagram, design, everything we will discuss in this video. Tabular column, results. Okay, yes. Before getting to the actual design or actual simulation, let's discuss some theory parts about this RC phase shift network. Okay, before getting to the actual phase shift oscillator, we should understand, we should know the basics of other our criteria, the Barkhausen criteria, a criterion for oscillators. Okay, what do you mean by Barkhausen criteria? Okay, let's discuss in this session. Here, I'm going to consider first in the first very basic, I'm going to consider basic inverting amplifier. We know what do you mean by inverting amplifier? Inverting amplifier will going to give 180-degree phase shift. You know the basic concept about inverting amplifier. What is the equation, output voltage equation for basic inverting amplifier? V not equal to A. A is nothing but voltage gain into VI. This is the uh, output voltage equation for basic inverting amplifier. Here, I'm going to give the basic inverting amplifier output to feedback network. Okay, feedback network. Okay, the input for this feedback network is nothing but V naught. Okay, and then output of this feedback is nothing but VF, feedback voltage, equal to here same what we taken here A, here beta. This is nothing but uh, feedback network factor. Okay, beta is nothing but feedback network factor, feedback factor anta karibodu. Okay, then here in the basic inverting amplifier, A into VI. What is the input for this feedback network here? V naught. So that's why beta into V naught. VF is nothing but feedback voltage equal to beta into V naught. Okay, yes. What do you mean by beta? Beta is nothing but gain, output divided by input. Here A equal to output V naught divided by VI. Here beta equal to VF divided by V naught. Here V naught is nothing but input for this feedback network. Okay, beta equal to VF divided by V naught. Okay, output divided by input, like that. Okay, yeah, and then this feedback voltage I'm going to give to the feedback to the fed. This feedback will going to fed to the a basic inverting amplifier. Here now I'm not going to give any external input supply for this basic inverting amplifier. Here VF input feedback voltage will going to act as an input voltage. VF equal to VI. VF will going to act as an input voltage for this basic inverting amplifier. That is the beauty of this RC phase shift network. Here we are not going to use any basic input supply. We are not going to give any input supply. Okay. Okay. Next, consider input voltage Vi at the input of the amplifier. The hence we get, you know, the basic equation V naught equal to A Vi. That is the equation number 1. Then beta feedback factor beta decides the feedback to be given to input Vf equal to beta into V naught. That is the equation 2. Then substitute equation 1 V naught equal to A Vi to this equation beta into A Vi here. Okay. Here we know we should know the basic Barkhausen criteria. Okay, what is the Barkhausen criteria? Here there are two criteria we should satisfy. That is nothing but total phase shift around a loop should be equal to 360 degree or 60 degree, 360 degree or 0 degree. Sorry, 0 degree or 360 degree. The magnitude of the product of the open loop gain. Okay. Amplifier and the magnitude of the feedback factor beta is unity. Magnitude of A beta should be equal to 1. This is the two criteria. One is nothing but total phase shift should be equal to 0 or 360 degree. Another criteria, magnitude of A beta equal to 1. That is the criteria. Here the criteria match act idea ಇಲ್ಲಿ? No. Here there is a and beta should be equal to 1. Then only the criteria will going to match. There is a criteria A beta equal to 1. If in case beta into A equal to 1, then VF equal to VI. Means VF will going to act as a input supply for our basic inverting amplifier. Here phase shift, the phase of VF is same as VI. That is, feedback network should introduce 180 degree phase shift, and then we know normal basic inverting amplifier will going to introduce another 180 degree phase shift, total equal to 360 degree. Okay, 360 degree output will going to generate without any input supply. That is the beauty of this RC phase shift oscillator. Without any input supply, RC phase shift oscillator will going to give 180 degree phase shift, 180 degree oscillation. Okay, we understand the basic Barbosan criteria, and then basic equation, how our feedback voltage will going to equal VI. Then we should understand this circuit diagram. Here I'm going to use one basic inverting amplifier, and then one RF means the feedback network. Here the circuit is very basic inverting amplifier. Okay, this is also inverting amplifier. Okay, complete inverting amplifier. And then for feedback, I'm going to use three RC network. First RC network RC, this RC, and then R1 and this C. Okay, total 3 RC network. Why we are going to use this feedback RC network? To generate 180 degree phase shift. Okay, total inverting amplifier will going to give 180 degree, another 180 degree. This RC phase shift network will going to give total 360 degree output will going to generate in the output side. Okay, then here phase shift oscillator consists of an inverting amplifier and RC phase shift network as shown above. The amplifier has internal phase shift of 180 degree. RC phase shift network consists of 3 capacitors and 3 resistors. RC network produces 180 degree phase shift. The total phase shift equal to 0 degree or 0 degree or 360 degree. Okay, yes. Then we should understand to obtain 180 degree phase shift in RC network, we should have inductive capacitance equal to √6 into R. Inductive capacitance equal to 1 divided by 2 pi f C. Okay, you can substitute f equal to 1 divided by 2 pi √6 RC. How this 6 will going to come? 6 is nothing but 2n. N is nothing but number of RC network. Here we are going to use 3 RC networks, so that's why 2 into 3. That's why this 6 will going to come. Okay, yes. Now the RC network which produce 180 degree phase shift also has attenuation factor of 29. Okay, RC phase shift will going to 180 degree, attenuation factor of 29. This means the amplifier must have voltage gain of 29 for the loop gain to become 1. Okay, means here the feedback network will going to generate 1 by 29. We know the basic criteria. Magnitude of A beta equal to 1 should be 1. So then our inverting amplifier should generate attenuation factor should be equal to 29. 29 into 1 divided by 29 should be equal to 1. So our criteria will going to match. Okay, yes. This is the design. Okay, RF equal to V0 divided by I1. I1 is nothing but 100 times of IB max. Okay, average current. IB max is nothing but average current for both terminal, inverting and non-inverting terminal. That is equal to 500 nano ampere. Okay, substitute here I1 equal to 100 into 500 nano ampere equal to 50 micro ampere. RF equal to V0 divided by I1. How this equation will going to come? Here there is a circuit. Okay, in the RF, across the RF circuit, you need to apply Ohm's law. RF is equal to V divided by R is equal to V by I formula. V is nothing but V0 divided by I. Okay, I1. Okay, here I1 is nothing but 50 micro ampere. Okay, next R1 equal to RF divided by R1. Okay, how this formula will going to come? I will going to tell in the future slides. Okay, AV equal to 29 we know. Okay, AV is nothing but AV is nothing but output divided by input, RF divided by R1. Okay, here you can substitute, that will going to come R1 equal to RF divided by 29. Okay, C equal to 1 divided by 2 pi root 6 FR. F is equal to, 1 divided by 2 pi RC root 6. Okay, here they are going to extract X. We need to find C value. Okay, okay. Now I'm going to discuss this problem here. Here, using a op-amp 741 op-amp with a supply of plus or minus 12 volts, design a phase shift oscillator to have an output frequency of 3.5 kilohertz. Here we know the basic output voltage saturation equal to they are going to mention input supply 12 volts. 12 minus 1 equal to 11 volts. Okay, I1 equal to 50 microampere. I already informed the information about I1. I already give the information. And now RF equal to V naught saturation divided by I1. V naught saturation is nothing but 11 divided by 50 into 10 to the power of minus 6 equal to 220 kilo ohm. Okay, and then R1 equal to how this R1 will going to come? Here there is a formula, ACL equal to 29. Okay, ACL is nothing but RF divided by R1. RF divided by R1 equal to 29. R1 equal to RF divided by 29. F is equal to 1 divided by 2 pi. Here R1 equal to 220k divided by 29, 6.8 kilo ohm is going to come. F is equal to 1 divided by 2 pi root 6 into R into C. Here everything we already know the values of everything, but we need to find out C value. So extract C here and then substitute the values and get the answer, that is nothing but 2730 picofarad. Okay, this is how we are going to solve the problem. This is the actual question. We should generate 3.5 kilohertz of oscillation here with the help of this design. Okay, here you need to substitute RF value 220 kilo ohm, and then R value is R1 is nothing but 3 R's. Okay, triple R, and then C value is nothing but 2700 C. Okay, in the feedback network we should substitute here. Okay, I'm going to show how to substitute. Here RF is nothing but 220 kilo ohm. R1 this RR is nothing but to 6.3 kilo ohm, 6.3 kilo ohm, 6.3 kilo ohm. C is nothing but 2700 picofarad, 2700 picofarad, 2700 2700 picofarad. Now we substitute the value. Okay, now we actually, I think all of you understand this theory portion and practical or problem about this oscillation network. Okay, now I'm going to show you how to simulate the circuit in the multisim platform. Okay, here already we made the circuit, but now I'm going to do separately for you guys. Now, okay, okay. First, we should select. We have to save. Then place component. Actually, we need 741 IC. Then registers. Four registers, RF and triple R. Next, capacitors, three capacitors, three. Yes, now VCC, VEE, and then ground. Okay, now. Okay, let's just simulate this circuit. Place the component first. R1 is nothing but RF. I'm going to connect here, and then 3 is nothing but non-inverting terminal, and then here first VCC. Control R, rotate, and due to the 4 VCC VEE, then this Next, this feedback network. Yes. Next, this triple C in the series order. Yes. Next, triple 6. Neatness. While connect the circuit, the maintenance of neatness is also maintaining the neatness also very important. Control R, control R, control R. Okay. Yes. Okay. The circuit is almost ready. Here I'm not going to use any signal generator. I'm going to use oscilloscope here. Give ground or negative negative. Okay, done. Almost circuit is done. A channel to 6. Okay, yes. What is the value of RF? You can change. You can change. R1 is nothing but okay, RF feedback resistance. Okay. Next here, triple R. This is nothing but only R or R1. Okay, R. This is nothing but another R. You can give any name. R1, R2. Okay. I'm going to use capital letter. R1. Okay. R1, R2. Yes. R1, R2. Okay. This is nothing but C1, C2, C2. Okay. What is the value of RF? RF is nothing but already we calculated the value 220 kilo ohm. 220 kilo ohm. Yes. What is the value of R? R is nothing but 6.3. I think yes. Right. 6.8. Sorry. 6.8 kilo ohm. These are also 6.3. Sorry. 6.8. 6.8 kilo ohm. Okay. 6.8 kilo ohm. Okay. What is the value of C? 2730. So 2700. You can use both. 2730. Okay. What is the advantage of this multi-sim? Otherwise, we actually done with hardware. Why we go for a software? Because we can use any value of capacitor or resistance value. Otherwise, in the laboratory, we didn't get this exact value. Okay, we need to compromise in the laboratory, but here there is no compromise. We can use any value and we can get exact output. Okay, without any errors. Okay, that is the beauty of this multi-sim or any software applications. Okay, yes, 2730. So picofarad, alva. Picofarad, small p. You should use small p. Okay, pico, close, pico. Okay, okay. Now I'm going to run before. What is the question? 12 plus or minus 12 volts plus what is the value of minus 12 minus 12. Okay, yes, the circuit is ready. Then run. We should wait for some time. Okay, the output is here. Okay, make reverse. What we should observe here? What is the question here? Okay, oscillation of, what is the question here? Output frequency should be equal to 3.5 kilohertz. Okay, how to measure this output frequency? Very simple. We should take the scalar points. You should keep here from 0. You can take any one full waveform. Keep here. Okay. What is the value here? 307.39 307.922 microsecond. Okay. What is the formula? Basic formula F is equal to 1 by T. 1 divided by 307.922 into 10 to the power of minus 6 is nothing but 3.2 kilohertz, approximately equal to 3.5. Okay, 3.2 kilohertz. There is a difference in the output frequency for theoretical versus practical. Okay, it's okay. 3.24 kilohertz. Okay, and then here one thing we need to observe, this is the first one. Okay, we should measure the frequency, time, and then it should be converted to frequency. Okay, that is the main agenda. Another one very important concept is here each individual RC network will going to generate 360-degree phase shift. Okay, 60-degree. Here first RC network will going to generate 60-degree. Another RC network will going to generate 60-degree. Total 120. This RC network will going to generate another 60-degree. Total 180-degree phase shift will going to generate with the help of this RC network. Okay, this RC network. Okay, now how to measure that 60-degree? Just you need to observe here. You need to observe here. Here connect this B channel to first RC network here. Okay, and then run. Okay, run. Okay, output will going to come. It will going to take some time. Okay, 120 seconds or 30 seconds. Then it will going to generate the output. Yes. Okay, here there are two waveforms. One normal output waveform, another one is 60-degree phase shift waveform. First you need to take here any one full waveform here, from here to here, one full waveform here. Measure one full one full box in horizontal. Each individual steps equal to 0.2. Okay, what are the full total steps here? One full cycle equal to what steps? Okay, measure here 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6. Okay, it will going to take 1.6 steps equal to 360-degree. 1.6 equal to 360-degree. 360-degree. Then what is the difference here? Here to here, you can take any one. Here to here, here to here, you can take any one. What is the difference here? 0.2, 0.3. Okay, 0.3. Okay, 0.3 equal to question mark. 0.3 equal to 0.3 equal to question mark. Question mark. Okay. Do the cross multiplication. 0.3 into 360 divided by 1.6. What is the output? 67.5. This is the answer. Okay, actually our each individual RC network will going to generate 60-degree, but here our RC network, first RC network will going to give 67. Okay, there is a difference. It's okay. Next RC network, step here, and then run. Okay, now same procedure. One full cycle equal to 1.6 equal to 360-degree. Here this 0.3 will going to change. Okay, yes. Okay, just hold the output and measure here. Okay, 0.1, 0.4, sorry, 0.3, 0.1, 0.3, 0.5, okay, means one step equal to 0.2, 0.4. Here this waveform is in middle, so 0.1 I'm going to consider 0.1, total 0.5, 0.5, 0.5 equal to question mark. What is the output? Do the cross multiplication. 0.5 into 360 divided by 1.6, okay, total 112, okay, exact answer 112. Actually it should give 120 degree, it's okay, 112. Okay, now I'm going to connect this output, this B channel to this RC network, okay, then run. We should give 180 degree phase shift now, exactly 180 degree phase shift, okay. Measure, please some time, wait for some time, okay, yes, okay, it will going to give exactly 180 degree phase shift. If there is a distortion, it's okay, it will going to give 180 degree phase shift. 0.1, 0.3, 0.5, point 7, 0.8, okay, 0.8, okay, observe here, 0.8. What is the value? Calculate 0.8 into 360 degree divided by 1.6, 0.8, okay, okay, exactly 180 degree, 180 degree, okay. This is how we should check the output. We check the output waveform for each individual RC network. The main agenda of this RC phase shift oscillator to generate to generate 360 degree output, 3.5 kilohertz. Another one we need to check how this RC network will going to generate 60 degree uh, phase shift for each individual RC network. Okay, this is how we are going to check. Okay, thank you so much, students, for listening this class. If you have any doubts, please let me know in the comment box. Okay, thank you so much. Anyhow, I'm going to give complete design in the description box. You can go through. I think there is no doubts in the design part. Okay, thank you so much.